So in our family of numbers, the rational numbers, terrific. All those rational numbers we can convert into fractions and so on. And in fact, that is the definition of a rational number. All right. So a rational number is any number that can be written as a fraction, basically. But A and B have to be integers. So, yeah, if you write root 2 over 3, yes, I wrote it as a fraction, but they're not integers, so it's not rational. And irrational then, well, it's just the prefix IR, and the prefix IR means not rational. Irrational, not rational. Okay? So if it can't be, all irrational numbers then are a unique, infinite decimal. Right? Has to be infinite, because if it terminates, then I can write it by saying, oh, well, it's this many tenths plus this many hundredths, and so on. So it will never terminate, and it will never repeat, because if it repeats, then as we just saw, we could turn that into a fraction as well. So it might repeat for just a little bit, but then it goes off into some other chaotic sequence of numbers. Pi, of course, is probably the most famous one that we know. Personally, my favourite irrational number is not pi, it's phi. The golden ratio, well done, yes. Do you know what phi is equal to? No, 1.6, closer to 1.6, but that's an approximation, of course. Okay, we're going to prove the square root of 2 is, in fact, an irrational number, and the method I'm going to use is proof by contradiction. May not be a proof that you're that familiar with. You mostly have done what we call deductive proofs, and you've seen them most often in geometry. And a deductive proof is one where you start with known facts, and from known facts you then deduce that something else is correct. That's what's called a proof by deduction. Another proof that we will look at in this course later on is an inductive proof. And that's where you assume that what you want to prove is correct and then go and show it's correct using your assumption. Okay? We'll see that later in the year. But another method of proof, which is not used that often, is proof by contradiction. And so we assume the opposite. We actually assume the opposite of what we want to prove. So I'm going to assume the square root of 2 is in fact a rational number. Now, if it is a rational number, then I can write it as a fraction. A over B, where both A and B are integers. And I'm assuming I've simplified this down completely, so A and B have no common factors. Okay? So they're integers, no common factors. Rearranging that, I get that B root 2 is equal to A. And I'm going to square both sides, so 2b squared is equal to a squared. Now, therefore, a squared is divisible by 2. It also means it's divisible by 4, because any square has to be divisible by squares. So if it's divisible by 2, it must be divisible by 2 squared. So a squared must be divisible by 2, because we're saying right here, it's 2 times something. They're the factors, 2 and b squared. So as I was saying, any square that's divisible by 2 is also divisible by 4. So therefore, a squared is divisible by 4. I know a squared is divisible by 4. So I could write a squared as 4 times some integer. But a squared is 2b squared. So 2b squared is equal to 4 times some integer, which means b squared is equal to 2 times some integer. So that means a squared and b squared are both divisible by 2, and thus must have a common factor. However, I stated that a and b had no common factors. That's a contradiction. So it can't be both. Therefore, my original statement must have been false. So the square root of 2 is not rational. If it's not rational, it's irrational. Voila. That's a proof by contradiction. So you start off assuming the opposite you want to prove, and go and you end up with some sort of contradiction. And go, well, hang on, can't be both. Therefore, my original assumption must have been wrong. So, anyway, so here we go, some questions out of 2B. Question 4 is getting you to do a proof by contradiction, but that one was square root of 3. Same sort of idea, but doing square root of 3 rather than square root of 2.